Hey, fellow mathers! Welcome to the podcast where math is figureoutable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
We know that, oh, for heaven's sakes. Hang on. My monitor's blinking on and off. I don't know why. I don't have this memorized. We know that algorithms are amazing historic achievements, but they're not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students and grappling with mathematical relationships.
We invite you to join us to make math more figureoutable. Okay, I have to tell you what I did. Why my monitor blinked. Because I was trying to roll up my sleeve and I hit the cord of my headphones and I think it pulled on the monitor cord. And all of a sudden the monitor was blinking. I was like, are we all going down?
When you were talking, I wasn't really thinking about your monitor anymore, but I do want to know, how many times do you think you've said the word figureoutable? I know, random.
Wow.
I was trying to estimate and I was like, no idea.
At least tens of thousands.
Yeah.
At least. Yeah. A lot.
I'm really not loving typing it. Sorry. It's a great word. Love the meaning.
It is fantastic. Yeah. In fact, it's funny because it's super easy to tell people our email addresses. Mm-hmm. Pam at mathisforgettable.com. Should I have just given that out to everyone? Anyway. But then if I have to type it, people hand it to me and they're like, here, type it. I'm like, oh gosh, math is figure. And then I always have to think there's an E on there, blah, blah, blah. Anyway, it's kind of funny. All right. Should we dive in?
Yes.
Diving in.
Last week we started some work with solving equations using a double number line as a model. And it really helps to make sense of location and how numbers are related. And as we said last week, we are going to continue that work today. I have my pencil.
Let's do it. Do it. We thank Chris Shore and his Clothesline Math. If you want to check out clotheslinemath.com, fantastic work there. So a double open number line has everything to do with, we're going to have relationships that we write on the top that then are corresponding to relationships on the bottom. And here we go. If you have not listened to last week's episode, may I highly recommend that you do, because I'm just going to build from it. Okay. So you could maybe get out of, you could stay with us if you want to, but you might want to go listen to last week's. If I was in a classroom where I had done last week's problem string with students, today I would remind them a little bit of what we did the time before. That kind of gives everybody access, especially if I had students who were absent or students who just need another go at some of what we just did. I would probably do x equals -6. So x is in the same location as -6. And then I would do the opposite of x is in the same location as -2. And so very much like we did in last week's problem string, I would put those on a number line and we would reason about where other things are. Like if this is where they are, where's 0? The opposite of x is here, where's x? So check that out if you haven't yet. But then the third problem would be, so you ready, Kim?
Yep.
What if I know that twice x or 2x is in the same location as 12? So what I wrote on my paper was 2x equals 12, but I'm also then next to it writing a big long number line, covering my whole paper left to right. Okay. And in the middle of that, I'm just going to put kind of randomly every time, not randomly, purposely in the middle of that number line, I'm going to put what we know every time. So every time I'm going to put what we know to start with in the middle. So I've put a tick mark in the middle of that number line and I've written 2x on the top and I've written 12 on the bottom of that tick mark. Okay. So if I know that, is there anything else that I know that you know? What else do you know looking at that?
Yeah. If I know 2x is 12, then I know 1x is 6.
Okay. So did you like scoot over some and write 1x equals?
No, I halved it. I thought, well, if double the x is 12, then half of it would be 6.
Okay, cool. So I might say let's find that on our number line. And maybe,
I just said half the x. That's not what I meant. Half of the double.
Oh, half of the 2x. Sure.
Yeah.
Okay. Sorry. Maybe a better facilitation might have been me to force where the 0 is. first. That might have been smart on my part.
Okay. All right.
So if 2x is in that location of 12, where would 0 be?
Very far to the left.
Okay, so very far to the left, I'm going to put a tick mark and I'm going to put 0.
Okay.
And I've got 0 on the bottom because that's where the numbers are going.
Yep.
So what goes on the top where the x's go? Any idea? If 2x is at 12, how many x's are at 0?
0 x's.
0x. Okay, so I'm just going to write above the 0. I'm going to write 0x. Okay. And then you had said, so right now on my paper, I've got sort of 0x on the left-hand side at 0 and 2x in the middle at 12. You said something about 1x.
And so it's right in the middle, in the middle between the 0x and the 2x.
And right in the middle of 0 and 12 is
6.
Okay, cool. So that's what my number line looks like. 0x is at 0, 1x is at 6, and 2x is at 12. Over there where I had equations on my paper, I've got 2x equal 12. Then I would say, and then we also know that x is at 6. We also could write that 0x is at 0. I don't know how interesting that is. Will that always be true? Will 0x always be at 0? We could think about that a little bit later. But cool. So I also might then say, how did you know where 1x is on the number line? So like once we had the 0x at 0 and the 2x at 12, how did you know to put the 1x where you put it?
Like right in the middle?
Exactly in the middle. Yeah. So like in the middle, do you mean you cut it in
half? Yeah. Yeah.
So then over there where I had the equations, I might say, well, so on the number line, I might say, oh, so it's like you cut the 2x in half. And over on the equations, I might just write underneath the 2x divided by 2, underneath 12 divided by 2, so that I can, it's like you cut them in half. You cut the 2x in half and you cut the 12 in half, and that's how you get x equals 6. So what I have written on the equations is actually describing the mental action that we did on the number line, but it will look a lot like when teachers just say, well, just divide both sides by 2. But rather than just divide both sides by 2, we're reasoning about the relationships. Okay, that one wasn't too hard, and that almost might have been too. Let's do a harder one so it gets a little bit more understandable why I'm putting on the number line.
Okay.
Because I can hear somebody saying, look, twice a number is 12. Pam, the number's got to be 6. Yes, but I want to kind of establish this distance thing because we're going to use it now. Okay, so next problem. What if 2x is in the same location as negative 12? So I'm drawing the number line, big long number line right in the middle. I'm putting 2x on top, putting negative 12 on the bottom. I'm going to ask you this time, where's 0?
It's going to be far to the right.
Okay.
Because I'm thinking about the negative 12 and I want 0 to be the right of that.
Okay. How far to the right? You said far. Just tell me.
It's the same as the number line above.
Okay, and how many units?
12.
12. Okay, so it's kind of arbitrary how long we're making 12, but okay. So now we know where 0 is, and
I wrote 0x above the 0, so above the line.
Okay. Is there anything else you know?
Yeah. So then 1x would be smack in the middle of the 2x and the 0x.
Okay.
And so that would be negative 6.
So it's almost like you're dividing that distance in half, and you're like, well, half of 2x is 1x, and half of negative 12. What is halfway between negative 12 and 0? Negative 6. Cool. So then over on the left, where I have 2x equals negative 12, underneath that, I'm writing, so we also know then that x is at negative 6. And I could, if I wanted to, sort of divide both the 2x and the negative 12 by 2. And I could kind of represent it that way. Nice. Hey, staying on that number line, we don't have to, but we could. I could also ask you where 4x is. I could also ask you where the opposite of x is. There's like lots of other relationships right now that we could start putting on that number line. And I might have wanted to have done some of that maybe in the last problem string that we did, or maybe here, just to kind of, so it's not always about finding x. It's like finding lots of relationships. And one of them could be finding x. Okay, cool. Next problem. How about if the opposite of 2x or negative 2x is in the same location as 10? So I've written negative 2x equals 10. I'm also drawing that number line. Right in the middle, I'm putting negative 2x on the top and 10 on the bottom. Where's 0?
Oh, that's kind of fun.
What's fun?
I've written a bunch of stuff that I would maybe want to use to help me. Okay. So I put negative 2x is in the same location as 10.
Mm-hmm.
And then I put 0.
And where's 0?
0 is to the left of the 10.
Okay.
10 spaces. And so I put, or 10, whatever span. So I put 0x on top and 0 on the bottom. And at that point I went like, what else do I know?
Yeah.
So I actually wrote -1x is 5, like in between what I had there currently. I don't know that
cut them in half. Bam.
Yeah, I don't know that I necessarily needed that for any reason, but I put it on there for funsies.
Okay. Sure.
And then I thought to myself, well, I know if I know where the opposite of 2x is, then I know 2x would be mirrored at the 0.
Like reflected over.
So I put 2x is -10.
So let me just, for everybody listening, right now on the right-hand side, we had -2x was in the same location as 10. So if you mirror that, you reflect it over the 0, then the opposite of -2x is going to be 2x, and the opposite of 10 is going to be -10. So I might over on the equations, we started with -2x equals 10. You also said that the opposite of x, or negative x, was at -5. So I've written that down. I've got -2x equals 10, -x equals -5. And then you said also that 2x is equal to -10. So we know all that right now. Super cool. All right.
But you're probably going to ask me about x. So then x would be in the middle of 0 and 2x.
Okay.
And in the middle of 0 and -10. So x is -5.
So x is in the same location as -5. Cool.
And what I love about what we're doing here is that, I'm going to find x, but I'm also exploring so many more relationships at the same time.
And actually kind of being clear.
Tinkering. Yeah,
you're tinkering. And Kim, when I started messing around with double open number lines and solving equations, I found myself doing mental actions that felt very much like the mental actions I do when I reason through numeracy problems.
Right.
And I found myself realizing that what I had always been doing with solving equations was much more of a do it mimic kind of thing, and not a reasoning using relationships kind of thing. And in that moment, I was like, I'm doing this. Like, we're going here. We are going here because, and then the more mathy people that I talk to, they're like, well, yeah, that's the kind of stuff that I'm actually doing in my head when I solve equations. And I was like, what? Why didn't you ever tell me that? Okay, cool. May I just suggest to everybody that for this problem, -2x equals 10, that's what we started with. I now have written -2x equals 10, -x equals -5, 2x equals -10, and x equals -5. I've got all of those on equations, and I've got all of those on the number line. I actually think that we kind of have two strategies happening here. So, Kim, your strategy to me feels like you started with the opposite of 2x equals 10, and you reflected that over to get 2x equals -10, and then you cut it in half to get x equals -5. Great strategy. You started with a -2x, you reflected it to get a positive 2x, then you cut it in half to get x. But you also could have gone a different direction from your starting point. You want to say what you were going to do, or what you could have done?
Well, tell me what I did. I think I did. Okay. I reflected it and then I cut it in half.
That's the strategy I would say that you actually kind of did. Yes.
So I could have cut it in half and then reflected.
Bam. And that's actually, I have that all up here on my number line right now because you had started with, well, I could do the -x equals -5. Then you kind of ignored it for a minute and did the reflection. So let me just talk through that. So starting from -2x, you cut it in half to get the opposite of x. -2x, cut it in half to get -1x. And then you reflected it to get x.
You know what I'm realizing? When we tell kids, just write it down and then divide by -2 or whatever, we're asking them to do the two things simultaneously. We're asking them to have it and reflect it.
Yeah.
And that's simultaneous is trickier for kids.
And it's not like we don't ever want kids to be able to look at -2x equals 10 and divide by -2.
Yeah, but if we wonder why that's
so confusing, so abstract,
maybe,
that's
probably why.
And why later, or maybe soon, negatives and coefficients and minus negatives and everything just gets so muddled because it's just all a bunch of rules that we really don't understand or have made sense of. So we're not grounded in being able to go, wait, what do I know? Not what have I mimicked, what have I memorized, but what do I know and how can I reason from there? Cool.
Guess who's doing some math when they get home from school today?
Fun. Let me mention one other thing. With the fact that we had two strategies here, that you could either reflect and then cut it in half, or you could cut it in half and then reflect. That was another moment where I was like, there's strategy.
Yeah.
Like so often solving equations is just do this, like get X alone. Like it's set, but now all of a sudden we can talk, hey, what do you want to do first? And now in the discussing of strategy, we're really building relationships. And that is what we've been doing in numeracy. And so when I saw that here, I was like, yes, we're going here. All right, next problem. What if, whole new universe, negative 2x equals negative 8, or the opposite of 2x equals negative 8? What I'm putting on my paper right now, right in the middle, is negative 2x on the top and negative 8 on the bottom. And Kim, before you say, let's let everybody listening, where's 0? So if you can picture negative 2x on the top, negative 8 on the bottom, where would 0 be? And go ahead, Kim, where's 0?
It's going to be to the right, a distance of 8.
Okay, cool. And if I want to find out where x is, what strategy might you want to?
This time I'm going to half first.
Okay.
I'm going to, so I put negative 1x is negative 4.
Okay.
And then I'm going to reflect that and call x 4.
So over there on the equations, I could write x equals 4. I could also write, in fact, honestly, I moved it down because I knew in the middle I was going to write the opposite of 1x equals negative 4. And then underneath that I wrote, so x equals 4. Listeners, I wonder if you can appreciate the fact that when I had negative x equals negative 4, it wasn't about multiplying by negative 1 or dividing by negative 1. It was really, well, if I know what the opposite of x is, then I know the opposite of that has got to be x. Like there's this whole opposite thing happening. I just encourage you to really think about the idea of using opposite and reflecting over that 0 to help you kind of make sense and help your students make sense of integer operations. Cool. I don't know. Often people can do one strategy and they can't really think of the other one. Can you think of the other one, Kim? Or I can run it. Like if we start from negative 2x equals negative 8, could you reflect first?
Yeah. So 2x would be 8.
Okay.
And then half of that, x would be 4.
Nice. So two different strategies that we could represent. All right. Super cool. Kim, I got one more kind of thing to do. Next problem. Okay. Ready? What if on the next problem, 1/2 of x equals 3? Okay. So I'm going to make a number line right in the middle. I'm going to put 1/2 x on the top and 3 on the bottom. And we're going to start with where's 0?
Do I have to?
Yes. Okay. Yes, you do.
All right. 0 is to the left.
Okay. Of 3, right? You're focused on the 3.
Yeah, left of 3.
Teachers, this is going to be the thing that might, the reason I'm forcing the 0 is it could be a really help. You don't always have to get 0. I mean, Kim probably didn't have to.
But it is useful to say that your distance is, like, otherwise it's just, when I want to go put x, it's not halfway between anything, you know? So fine, I'll write it down. But yeah, but it gives some relation to why half. Why is it half x? So I put my 0 to the left.
Okay.
And then I put x and 6 to the right, and my half x that I started with is smack in the middle. Because
if x is at 6, then half of that distance would be in the middle of 0 and 6 of 3. Cool. So it's almost like to put the x there, you almost like had to double that distance from 0. That could be a way of thinking about that. So on the paper, I could have that 1/2 times x equals 3, and then I could literally double the 1/2 x to get x, and then we doubled that distance of 3, double the 3 to get 6. Again, the kind of notation that I'm making could look like it's kind of what we tell kids to do when they're balancing an equation, but really the relationships I'm having in my head are much more about relationships and not just like mimicking a thing to do. Cool. Next problem. What if I know that 1/3 of x is at negative 2? So drawing my number line right in the middle, I've got 1/3 x on the top, I've got negative 2 on the bottom, and I am going to force where's 0?
Yeah, and I actually almost started putting it to the left of negative 2 because I was focused on the 3rd. So I put it to the right. So
because negative 2 is to the left of 0. Okay.
And so if 1/3 is a span of 2 1/3 x, then I know I want x at -6 because I need 3 of those 1/3. So I'm tripling the 1/3 to get to x, and I'm tripling the -2 to get to -6.
Okay, and I believe you. I'm going to slow that down just a little bit because you know what kids, almost every kid I've done this with does? They look at that
They put in
1/3
2/3?
x. They do.
Okay.
They look at that 1/3 x and it's 2 away from 0 to the left. And they go, well, I know where 2 1/3 x is. And so they go over another 2 units. They put a tick mark and they put 2/3 x. And then they're like, well, if the 1/3 x was at -2, then 2 1/3 x would be at -4. And then you know what they write? They write 3/3 x above the -6.
And I would
go ahead. Good.
I would argue that kids who are multiplicative thinkers with number probably do this additive approach because it's something new. It's something new they're thinking about.
And then they fairly quickly start thinking about, oh yeah, I could just like scale up. I need 3 of those 1/3. So I'm going to scale that. But boy, at first, it's super interesting to let them be a little additive first. And then kind of that thing we started with last episode and a little bit today, what else do you know? And it's okay for them to stick in that 1/3 x or that the 2/3 x, however many x's they need, totally legal to do. And so I think you just found that x was at -6. So I would make sure that I have that written there. Go ahead.
When a kid puts the 1/3 to start and then they step up the 2/3, 3/3, in that moment, are then you scaling, like in your summary of what they did, are you showing scaling marks as a nudge? Or?
So I think it depends on the grade level I'm working with. So if it's younger grades and that means I have a little more time, then I probably wouldn't yet. I would probably kind of leave. I would do the next problem. We would do some more. And then I would look for generalizations about how we got from, how did we get from 1/2 x to x? How did we get from 1/3 x to x? How did we get from 1/4 x to x?
Yeah.
Oh, every time we needed 2 1/2s and 3 1/3s and 4 1/4s. And I'm like, oh, we're scaling. So I would sort of build that scaling. If I was working with older students, hopefully who owned more multiplicative thinking, I'd get there a little faster.
Okay.
Yeah, I might do it right here.
Yeah,
cool. Okay, next problem. What if I know that it's actually the last problem, so you can do it, everybody. Hang in there. What if out -1/4 x equals -5? -1/4 x equals -5. So Kim, stop right now. Tell me right now what you've already got written. Don't answer anything, but just like, what did you immediately start doing? I'm just curious.
I put 0.
Okay, cool. Did you also put the -1/4 x in
Oh,
location?
Yeah, I put 1/4 x on, drew a line, put -1/4 x in the middle at the top and -5 at the bottom. And then I put 0 and 0.
Okay. 0 and 0 x. Okay. All right. What else do you know?
And then I reflected first. And I put 1/4 x is 5.
Ooh, nice move. So 1/4 x.
And it's
is positive 5. Yep. Because -1/4 x was -5. Okay.
And then if you'll let me, I'm going to scale.
Okay.
4 times.
She'll need 4 of those 1/4.
Yep. So 4/4 x, which is 1x, is 20.
Is 20. Nice. Could you imagine that somebody might have not reflected first? That they might have gone from that -1/4 x in the same location as -5 and found -4/4 x?
Yeah, that'd be -20.
That'd be -20. And now I've got -x at negative, or the opposite of x at -20, and reflect that over to x is 20. And by calling on and representing both of those strategies, I think students are getting more clear at lots of things, not just getting an answer to solving an equation. You took a breath. What were you
saying? I'm wondering if when I encountered a problem, would there be times where I prefer, based on the numbers, to reflect first and then scale, or if I would want to scale first? I'm sure there are times where.
Well, we'll throw that out as an open question. Let everybody think about that. So, Kim, what are a couple of things that are happening? I'll just mention operator meaning of fractions. Just came into that last bit. 1/4 of something, 1/3 of something. So if you wanted to do a little bit of work before this, you might actually have done some operator meaning of fractions strings to get kids thinking about the operator meaning of fractions. That could be a kind of lead in. But yeah, There you go. Solving equations where the goal isn't just to find X. The goal is actually to build algebraic reasoning along with additive and multiplicative reasoning and proportional reasoning, because we're on the double open number line. So lots of things kind of embedded, but we're building kids mathematizing.
Yeah. And it's kind of fun, right?
And it's kind of fun.
And as a younger grades teacher who does work on a number line, it's super fun to know that a model that we're building doesn't get left behind.
Nice,
middle school teachers hopefully are capitalizing on that work.
Yeah.
Okay. So earlier Pam shared that all of our emails now. So we would love it if you would email me, Kim@mathisfigureoutable.com, and you can share a review. You can leave it on the podcast. Tell us what you want to hear about. Ask a question. Tell us a funny thing that's happened in your class so that we can share it with you.
Yeah, and thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com and keep spreading the word that math is figureoutable.